Alright, in this video here we're going to do an example of simple harmonic motion where we are given a word problem and we actually have to write the function that models the simple harmonic motion and then also sketch the graph of that function after we come up with the actual equation itself. Alright, so here's our problem situation. Alright, a mass is suspended from a spring. The spring is compressed 4 centimeters and then released, and the mass will return to its compressed position after 1/3 of a second. Right, and we're asked to find the function to model that displacement. Now, if you didn't watch the other video that I did on simple harmonic motion where I explained the formulas for simple harmonic motion and what everything represents, you probably should check those out before you watch this one. This one we're just going to apply those formulas and use them to do this problem. Right? But in that other video I explained in a little more detail what the formulas actually represent. Alright, so let's draw a little picture about what's going on here so that we make sure we choose the right function. Because we can have simple harmonic motion with a sine function or with a cosine function, so we just need to make sure we choose the right one based on this particular situation. Right, so we have a spring that's compressed, so let's say this, we're hanging from a spring here. It's compressed 4 centimeters and then released. Right, so I have a mass hanging from a spring. If this is its rest position here, this dotted line is the rest position, it's being compressed 4 centimeters before we release it. Right? So, if you just let the mass hang there, that would be the rest position. What we're doing is like picking it up 4 centimeters and then letting it go, and that's going to make it bob up and down. So if it's starting 4 centimeters above that rest position, it's also going to drop to its lowest point, will be 4 centimeters below that rest position. Right, so we're pushing it up 4 centimeters and then letting it go. It's going to drop down and then drop back up, or not drop back up, that doesn't make any sense. It's going to drop down and then go back up. And the time it takes to do that, to go from the starting point all the way down and all the way back up, is going to be 1/3 of a second. Right, that's that last thing they tell us. All right, so this is not a technical way to draw this situation. This is just the way I understand it. Right, we have a mass hanging from a spring. The dotted line represents my rest position, which is we just like let it hang there and let it kind of find its equilibrium. That's where it's going to hang to. I compress it 4 centimeters up and then let it drop, and it's going to bounce up and down. And it takes 1/3 of a second to go all the way down and then all the way back up. All right, so we want to find a function to model this displacement. So our first choice we have to make is, do we use a sine function or a cosine function? Right, remember the graphs of sine and cosine. The sine function starts at the origin. The cosine function starts at 1. It starts at the maximum point. Well, in this case, since we are compressing that spring before we let it go, the spring here is starting at its maximum displacement. Right? It's starting up 4 centimeters when we start the clock and let it go. Since it's starting at that maximum position, we're going to use the cosine function to model this. Right? We use the cosine function if our starting position is at that maximum displacement. If we were to just let it go here at its rest position and then just drop it from there and let it start bouncing up and down, that would be modeled by the sine function, because the sine function starts on that middle value, that rest position. Right, so hopefully this picture makes sense as far as why we choose one of these over the other. Right? If it was starting on that dotted line, that would be the sine function. If it's starting up at the top, well, the cosine function starts up at the top. We need to use cosine. All right, so that's our first thing, is we know we're using a cosine function, so that's not so bad. All right, so it's going to be y equals, I'm going to leave a little space because I need to put a number in front of the cosine. Right, and that number in front of the cosine is my amplitude. Right, remember, amplitude refers to your maximum displacement. Well, this 4 centimeters here, that's my amplitude. I was going to write amp, and then I put too many letters, so I'm forced to write the whole word there. All right, so amplitude, that's how far above and below that rest position we go. And here, if we're compressing the spring 4 centimeters to its maximum point, well, that's the amplitude, is those 4 centimeters. All right, so my amplitude is going to be 4, so it's 4 times cosine, and then, maybe I should put up the actual formula here, right? It's y equals a cosine omega t, right? The a is our amplitude, which we just talked about, that's our 4, and then we have to put in an omega here, right? Remember, the omega comes from the period of my function, right? And the period is equal to 2 pi over omega. Right, now, where these formulas come from, I said at the beginning of this, I did another video where I talked about the simple harmonic motion and the formulas for it. That's where these formulas are coming from. So if you have no clue what I'm talking about here, maybe pause this one, go watch the other video that I did on simple harmonic motion, and then you can come back to this one, and it'll make sense when I say that the period is equal to 2 pi divided by omega. Right, where omega is that number inside the cosine function multiplying the t. Right, well, my period is how long it takes to do one full cycle, and they tell us it returns to its compressed position in 1/3 of a second. All right, so we compress it, it goes all the way down, all the way up. That takes 1/3 of a second. 1/3 of a second is my period. All right, so I can say that 1/3 is going to equal 2 pi over omega. All right, and now I need to solve this equation for omega, because omega is the number that I need to plug in here next to my t, right, inside my cosine function. So if I have 1/3 equals 2 pi over omega, I need to solve for omega, right? So when you're doing one of these word problems and you have to actually write the function yourself, you have to first find the amplitude, right? That's your A. That's usually not that hard to find from just reading the problem. How far above or below the rest value does it go? In this case, 4 centimeters. That right there is my amplitude. To find the period is a little bit trickier because there's a formula for period. So you have to set the period, whatever period they give you, in this case 1/3 of a second, set that equal to the formula 2 pi over omega, and then solve for omega to give you the number that you need to plug in here. All right, so to solve this, when I have those two fractions equal to each other, I cross multiply. All right, I multiply the omega up here times the 1, so I'm going to get omega equals, and then the 3 I multiply times the 2 pi, and that's going to give me 6 pi. And since I multiply the omega times 1, it's already solved for omega. Omega is equal to 6 pi. Right, so it's going to be y equals 4 cosine of 6 pi t. All right, so once I solve for that omega, that's what multiplies the t inside of my cosine function. All right, so that's the function that's going to model this harmonic motion of this mass suspended from the spring. Right, it starts at the maximum amplitude, which is why we choose the cosine function. The maximum amplitude is 4, so that's the number I put out here, and it takes 1/3 of a second for it to do one complete cycle. So I do the 1/3 for my period equal to 2 pi over omega, cross multiply that to solve for omega. Omega equals 6 pi, that's the number I plug in there. Right, so once you do one or two of these, you start to get the hang of it. The key thing is deciding, is it a sine function or a cosine function? Remember, the key difference there, cosine starts at the maximum position, sine starts at the rest position, in the middle, right? So if you keep that in mind, then it's not that hard to figure out which one it's going to be. All right, so that's part A, finding the function to model our displacement. Let me erase all this work I did here so that we have room to do the second part, which is to sketch a graph of the function. Now, when I'm sketching a graph of the function, I'm not going to go to that function that I just wrote up there and try to figure all the stuff out from the graph. I already have all the information I need from the word problem, from this little thing I drew over here, right? The maximum displacement is 4 centimeters. So I'm going to put a line up here and call that 4. I'm going to put another one down here and call that -4. Right? And I know my cosine function starts at that maximum point, right? So starting up at that 4 centimeters. And then the period is 1/3 of a second. So over here, I'm going to make 1/3 of a second, and then I'm going to cut that into 4 pieces. Right, remember, for the sine and cosine functions, you can kind of graph them by splitting one period into 4 equal pieces. And then for the cosine function, you start at the high point, and then you hit the middle point, and then you hit the low point, and then you're back to the middle, and then at the end of the period, you're back up where you started at the top. And if you just connect those, you get your graph of one period. And then if you want to do that again, I'm not going to make all the marks here, but if you do that again, between 1/3 of a second and 2/3 of a second, you have another full period where the graph hits those same points all over again. And if you do that a third time, you just keep repeating that same pattern over and over again. Right? So that's our graph of this function, y equals 4 cosine 6 pi t, which models a spring that's compressed 4 centimeters, then released. And then it takes 1/3 of a second for it to return, which you're looking at the graph. It starts at 4, it goes down, all the way down, comes all the way back up. After 1/3 of a second, it's back up to the top where it started. Right? It all fits together. It all makes sense. Right? Now, one thing we didn't mention here that I did mention on that other video, the frequency. Right? What is the frequency of this harmonic motion? Remember, the frequency is the reciprocal of the period. If the period is 1/3, the reciprocal of 1/3 is 3. Right, which means this thing is going to go up and down in 1/3 of a second. It's going to go up and down again. That's going to be 2/3 of a second. When it goes up and down a third time, that's 3/3 of a second, which is 1 second. Right, so this mass is going to go through 3 cycles in 1 second. Right, because its period is 1/3 of a second, I can do that 1/3 3 times in a second. Right. So the frequency here, this question doesn't ask us the frequency, but a question you do might someday ask you the frequency. Is the reciprocal of the period It's how many times you go through that full cycle in 1 second, which if you graph this and you keep on going until you get to one hole, you'll see it does 3 full periods in 1 second. So there's your frequency. All right, so that's simple harmonic motion. Reading the word problem, being able to write the equation from that, understanding what the parts of the formula mean, all important things in order to be able to do this type of problem.